Hey everybody, Professor Monty here. Today what we're going to do is we're going to learn some more techniques on integration, specifically substitution. Now, what substitution is, it's going backwards from the chain rule with differentiation. So let's say this. Recall in differentiation, which means taking the derivative, when we had an inside function. We had to use the chain rule. With integration, we'll say and an inside function. We need to use substitution. And the idea is we substitute whatever the chain rule would be taking that additional derivative of. We typically use the letter U to represent, we'll just say the inside function. All right. That's actually the end of the lecture for this section. The rest of the section is just showing you examples, what we're talking about. So let me show you what inside functions are, and then we'll actually jump in and do problems. So just as a reminder, because we've seen this before with the chain rule. So examples, well, let's just write this up. Examples of inside functions. So one, suppose we have f of x equals, and then we have something to a power. Well, we know that is the inside function. Suppose we had a square root or a cubed root or any radical at all. Well, whatever's inside here, that's the inside function. Let's do a couple more over here. Suppose I had h of x is equal to the ln of something. You know what that something is? You're right, it's the inside function. And then we'll do another one. This one's kind of tricky because it doesn't really look like an inside function. Let's call it k of x. But it's when we have e raised to some power. And the reason that doesn't always look like an inside function because they don't always have the parentheses there. Say that was just e to the 5x. Well, you wouldn't put a parentheses around the 5x. Obviously, you would if it was 5x plus 2. But that is the inside function as well. And that's pretty much all inclusive. Notice 2 I didn't really have to put because we could write the square root as the 1/2 power. So that's just a special case of the first one I did, f of x. All right, so anyway, let's go through it. Well, we'll do a couple of the easier examples, and then we'll throw some other things in there. Okay, so the first thing I want to do, and I'm just going to call these examples. I'm not going to number these because if we have a different version of the book, a different edition, it might be a different number. So I've got the integral. Inside parentheses, it says x squared minus 7. That's to the 6th power, but then it's times 2x with respect to x. I'm going to get rid of that dot in the book. They don't have the dot there. It's just, we just know that's multiplication. Okay, but again, notice, and let me make this a different color. Let's go blue. So this is, of course, my inside function. So what I'm going to write is I'm going to let u equal x squared minus 7. Now, I'll show this to you the first couple times. If I take the derivative using Leibnitz notation, du dx is equal to 2x. Now, remember what we've seen before when we talked about this, is that du is really equal to 2x dx with respect to x. So we don't need, you can kind of think of that as multiplying both sides by dx. That's not technically, literally what we're doing, but du is equal to 2x dx. And what we see is this 2x dx, let's use another color. This 2x dx we see right here. So that is just going to become du. The x squared minus 7 becomes, here let's circle in blue, notice that the x squared minus 7, that's just equal to u, and then it's still raised to the 6th power. We'll circle the u in blue because that's where it came from. And so now we have the integral of u to the 6th du. We have to get that du there because u is now the new variable. We couldn't do u to the 6th dx because that would imply x is the variable and u would have to be a constant in that case. So we have to get it in terms of, once we make that u substitution, we have to get a du. But that's nice because u to the 6th du, that's simple to integrate. I just go u to the 7th, multiply by the reciprocal, and then put my plus c. I'm almost done. The only reason I'm not done is because the problem's supposed to be in terms of x, not in terms of u. So now I just replace that. So we'll put a couple of equals here. So this just becomes 1/7. Remember, u was x squared minus 7. And now I'm done. As always, we can check by taking the derivative. Let's just check real quick on this one because we haven't done one of these and this seems kind of weird. So think about taking the derivative. I'm going to bring that 7 down in front. So I've got that 1/7 constant multiple stays, but then I'm going to say times 7 x squared plus 7 to the 6th, but then times 2x from the chain rule. And then this constant out here goes to 0. Well, the 7 and the 1/7 cancel. I just get x squared plus 7 raised to the 6th times 2x. And in fact, let's look back at our problem. That is exactly what I have up here. And we'll use this other colored pen. This was what I started out with. So I know, in fact, oh, I did it correctly. That is, in fact, the antiderivative or the integral of x squared minus 7 to the 6th times 2x. Okay, so there's one. Let's do another example. I know there was a lot going on there. That's why we're doing a bunch of examples. And another one will be pretty straightforward like this one. I won't add that step of checking the derivative. You probably should to make sure you have the right answer. I'm not, just because it makes it look like a more complicated problem. Okay, let's do another example. All right, let's see. This one's the integral of, it's going to look very similar to the last problem because I want these to look similar so that you say, hey, yeah, we've done one like this. This just works a lot like the last one. So it's 2t to the 5th minus 3, but on the outside we have times t to the 4th with respect to t. All right, again, we look at the inside function. Here's the inside function. I was going to do that in blue. Oh, here, let's erase the one that I have. Here's the inside function. So I'm going to let that be u. So I'm going to say, oh, let u equal 2t to the 5th minus 3. It's not a minus, minus 3. Again, when I take the derivative, du dt, because t is the variable, I get 10t to the 4th. The minus 3 goes away. But what we're going to do from now on we're going to say, oh, the du is 10t to the fourth dt. We're going to skip that middle step. We'll just go straight to du. Okay, now here's where a little bit goes on. We know this blue, right? That was the 2t to the fifth minus 3. That's equal to u. So let's just replace that with a u. So I know I have u. We'll put it in parentheses just so we see that. Underline that in blue. But that t to the fourth, notice here we have t to the fourth dt, but over here we have a 10 t to the fourth dt. So what I need to do, I need to get a 10 there. So here's how I'm going to write this. I'm going to put, well, here, let's put that back in black here. The t to the fourth dt, but I need that 10. So I'm going to put a 10 here so that I have 10t to the fourth dt, what I have circled over in the green. But I can't just arbitrarily put a 10 there unless I undo the 10 somehow. The way I'm going to undo it is I'm going to put a 1/10 out here. And now when I do it, everything that's circled in green is going to become du. So now what I'm going to have is 1/10 u, we don't need the parentheses anymore, du. This du, again in the green, was the 10t to the fourth dt. So I just made that, well, that's not how I wanted that to work. Oh, I still haven't gotten to the eraser. Let's try this again. There we go. Okay, so this du was just the 10t to the fourth dt. I had to do that little trick with the 10 and the 1/10 on the outside. But again, I've got u du. I know how to integrate that. That's actually very simple. It just becomes u squared. So I've got the 1/10. This becomes u squared. Oops. Let's make a little room there. Let's erase all that. This becomes u squared multiplied by the reciprocal, and then put plus c. And notice I'm not putting a parenthesis around that whole thing. Technically, that c would be multiplied by 1/10, but 1/10 of a constant is still a constant. We don't know what the value of the constant is now. When I multiply by 1/10, I still don't know what the value is. So I can just still call it a constant. So I get 1/20 u squared plus c, and then I'll resubstitute what u is equal to. And remember, u is equal to 2t to the fifth minus 3. T to the fifth minus 3 squared plus c. So all I did is I replaced the u with 2t to the fifth minus 3, because that's what we said u was equal to. Again, you can multiply that all out, make sure that it works. I'm not going to this time because there's enough steps going on here, especially with that 10 and that 1/10 that threw us. Okay. But again, we'll do more practice. This still might be kind of confusing. You still might be saying, I have no idea what's going on. That's okay. That's why we're going to do a bunch more examples to get it a little more clear. If it's still not clear at the end of the lesson, then just go back through and go through it again. Remember my suggestion, look at the original problem I put, try to go through as many steps as you can with the tape paused, and then see if you can get through the whole time, or if you get stuck, what the next step should have been. Okay, so here's my next problem. Oh, I didn't want blue. Here's my next problem. It's the integral of ln of x, oops, ln of x, good heavens, raised to the 7th power. I need to erase that. That just doesn't look like a parentheses to me. times 1 over x dx. And they tell us x has to be greater than 0. The only reason they're saying that is because I have ln of x without the absolute value. And remember, you can't take the ln of a non-negative number. So you can't take the ln of negatives or of 0. So x has to be greater than 0 in this case. But again, inside function. There, ln of x is my inside function. So what I'm going to say is I'm going to say, okay, let u equal ln of x. And then du, remember the derivative of ln of x is 1 over x, but it's a different variable, so we say dx. Okay, now we often, when we take the derivative, we'll say the absolute value, and we certainly could in this problem. There's no harm in saying the absolute value, but remember x is greater than 0. So 1 over x has to be greater than 0 anyway, so the absolute value is non-essential. It's redundant. Okay, so let's see what we have. So this 1 over x dx, we have exactly 1 over x dx. So that just becomes du. So that's going to become my du. We'll circle that in green so we know those match. The ln of x to the 7th became, remember ln of x, that was u. That just becomes u to the 7th. Underline that in blue. Now, again, we're all in terms of u, so now we just integrate. Oh, that's 1/8 u to the 8th plus c. But u is equal to ln of x, so it's 1/8 ln of x raised to the 8th power plus c. And I'm done. That was not so bad. You can try that out. So that was a very quick problem. But we'll just keep going. We'll do some more examples. I've got plenty. Well, I think there's plenty. You may say, I want more examples. But you don't get any more. You can come to the live session and ask for more examples if you'd like to. So this time we have e to the 7x dx. Ooh, we haven't seen one like this before. That 7x, that exponent, is the inside function. Because remember, if I did the derivative of this, I'd do e to the 7x, but then then times the derivative of 7x. Chain rule. Well, so since that 7x is where the chain rule gets applied to, that's my u substitution. So we're going to set let u equal 7x, and then du equals 7 dx. And again, this is one of those where I don't have a 7. A lot of times what people will want to do is they'll, at this point, say, you know what, let's put the 7 here so I have the 7 and the dx, but we have to counterbalance that with a 1/7 here. I don't really like writing it on the original problem, so I'm going to erase those and just put it on the next problem. In the next step, rather. So I've got e to the 7x dx, and now I'd say, oh, put a 7 there and a 1/7 there. So those cancel each other out, but the big thing is this 7 dx, it's right there. Both of those get replaced just with du. So those become du. I still have this 1/7 on the outside, and I have the e to the 7x. Well, e to the 7x, right? 7x is just u. So I'm going to replace that with a u. And so now I have, that 7's gone, right? It left with the dx. I have e to the u du. And that u was 7x. And now again, we just integrate. We know when we integrate the integral of e to the u, the antiderivative of e to the u is just e to the u. So I go 1/7. Didn't want to do that in blue. I do 1/7 e to the u plus c, which is 1/7. Now I resubstitute e to the, what did I let u be? 7x plus c. And I'm done. Again, we haven't checked one of these in a while, so let's check real quick. take the derivative, and a lot of times you can do these in their head because they're not terribly complicated. So if I do the derivative of 1/7 e to the 7x plus c, I get 1/7 constant multiple, e to the 7x, because it's an exponential, I get the whole thing back, but then times 7 from the chain rule. That was the derivative of the 7x. And then plus c goes to 0. But then the 7 here cancels with the 1/7 here. And I just get e to the 7x. Well, is that what the original problem was? Sure was. So notice here, this e to the 7x was exactly what I started taking the antiderivative of. Okay. I'm going to erase that circle so that when you're going back through it, you don't say, why in the world is that circled? So I'll erase that. I'll erase this. We will just say, check, that it did in fact check. But that's what we're checking. When I take the derivative, it should be what we're taking the integral of in the first place. Okay, so let's jump a little bit further. This is problem 22, but I'm not telling you what problem it is. A little too late on that, isn't it? So we'll call it example. It is problem 22 in this book. And this one looks a little bit different. We haven't seen one of these before. It's got a dx on the top and a 1 plus 7x on the bottom. Well, what I want you to realize is that dx on the top, we can rewrite that just as 1 over 1 plus 7x, and then put the dx on the outside. And this may not look familiar to you, but you should get to the point where it does look familiar to you, because remember, if I integrate 1 over x dx, I get the ln of the absolute value of x. And that's what I want to see when I look at this, is that, oh, that's 1 over something with an x to the first. So this piece down here, that's going to be my u-substitution. That is kind of this inside function right here. I'm going to erase that circle around the x because I don't want you to think that's what, in this problem, what we're doing is using u as the x. We're using u as the 1 plus 7x. So let's do this. We'll kind of, this is kind of an aside. Okay, but what we're going to do, kind of out of room here, we're going to let u equal 1 plus 7x. And then du is just 7 dx. So what I get is that becomes 1 over u. Notice also I don't have the 7. I need a 7 dx, so I'm going to do what I did before. I'm going to do 7 on the inside, 1/7 on the outside. Those multiply those together, they cancel out. But this 7 dx is right here. That whole thing just becomes du. Notice the 1/7 is still there. Move this over a little bit. I still have the 1/7 out here, but the 7 and the dx just become a du. And again, now I can integrate. I get 1/7. 1 over u becomes the ln of the absolute value of u plus c. Or resubstituting ln of 1 plus 7x plus c. Okay, so I've done a bunch of examples. I'm going to do a couple more, but what we're going to do is we're going to put limits of integration. So rather than getting the family of all the antiderivatives, we're going to actually plug in values and get a numeric value for these. We still are going to have to use the u-substitution. We're just going to have that other step of using the fundamental theorem to plug in the limits of integration to get a value. Okay, so here's the next example. Let's see, it says, the integral from 0 to 1, 3x squared, e to the x cubed with respect to x. And there's a lot going on here. Notice if I was taking the derivative of this, my first thought is, oh, that's a product rule, because I've got the e to the x squared times e to the x cubed. But in addition, I've got a chain rule, because the derivative of e to the x cubed is e to the x cubed times the derivative of the exponent, 3x squared. Oh, chain rule. As soon as I think chain rule to take the derivative, I think, oh, this whole thing is going to be u. And in fact, let's see what happens. That's my inside function. Let u equal x cubed. Then the derivative of that is 3x squared dx. Again, this time they're being nice to us, because the 3x squared dx, we do have the 3x squared. Wasn't a very good circle. We have all of the 3x squared and the dx. So all that is just going to become du. All right, so let's see what we have. We have the 0 to 1. The 3x squared dx just became du. We'll put that at the back. The e to the x cubed, remember x cubed was e. That's just e to the u. Wow, that really simplified nicely to take the antiderivative. The integral of e to the u is just e to the u. Oops, no more integral, I'm taking the integral. So I say, oh, that's just e to the u. I don't have to put plus c here because I'm integrated from 0 to 1. Now, we have to be careful. That 0 to 1 up here, where we started, that 0 to 1 is in terms of x. It's not in terms of u. So now I have to resubstitute. And so remember, u is equal to x cubed, so we resubstitute just like we did. So now it's e to the x cubed from 0 to 1. Now I can plug the 0 and 1 in. So I plug in the 1 first, minus, then I plug in the 0. Doesn't really look like a 3. So I get, well, 1 to the cube is just 1. So I get e to the 1 minus, and 0 to the third is just 0, minus e to the 0. We usually write e to the 1 just as e. E to the 0 is equal to 1 itself. That's my exact answer. I can plug it into my calculator and see what I get. We know e is about 2.7, so this is about 1.7. If we want to go to more decimal places, we could. Let me grab my calculator real quick. And if I go e to the first power and then minus 1, it's about 1.718. If we want to go to 3 decimals, we could. But that's the idea. Remember, that's one of the common mistakes is students will do their antiderivative of e to the u and find out what that is and then plug in the limits of integration. In this case, it wouldn't have changed anything because if you did, 0 cubed and 1 cubed are still 0 and 1. But those are the only two numbers that when you cube them, you get the same number. I guess -1 cubed is -1 also, but any other numbers, that wouldn't have worked. And in the next problem, it wouldn't work if I forgot to do my resubstitution. All right, so let's just do one last example. And that's going to be, what, 2, 4, 7 examples of u substitution. So hopefully that's enough to at least get you started. And then 2 of them will be with limits of integration, so we find a value. Okay, so this one is the integral, we'll call it example, from 1 to 2, x times x squared minus 1 raised to the 7th dx. We sure have a lot of 7th powers in this problem. A lot of 7s going on. So now when I work this problem out, again, identify the inside function. That's the inside function. So that's what we're going to have equal u. So let's say let u equal x squared minus 1. And then take its derivative, the derivative of that, du is equal to 2x dx. And again, look up there. I have the x. I'm going to go down to another line. So if I do x squared minus 1 to the 7th dx. Well, first of all, I know that x squared minus 1 is just u. So this x squared minus 1 just becomes u. So that becomes u to the 7th. I have this x and the dx, but I need a 2x. So I'm going to do my little trick. I'm going to put the 2 right there, but I have to put a 1/2 on the outside. Oh, now I've got my 2x dx. That's circled becomes the du. Should I circle that in green? I still have on the outside that 1/2, so it's still, I wanted to go back to black. It's still 1/2 times the integral from 1 to 2 of u to the 7th du. Everything else got replaced out. And so I go that next step. Let's integrate that. So now it's u to the 8th. So now I have a 1/2. That becomes a u to the 8th. I have to multiply by the reciprocal 1/8. And then I'm saying, oh, I'm integrating from 1 to 2. So now I'm just going to integrate that. First, we need to make our substitution. So I have 1/16. It's not u to the 8th, it's x squared minus 1. That's what I'm integrating from 1 to 2. So now I plug in the 2, then I plug in the 1. Now the 1/16, you have your choice. You can just leave it on the outside and then plug in the 2 and plug in the 1. I'll just do it all at one time. So I plug in the 2, minus, then I plug in the 1. That's where I said the 1/16. You can just do 1/16 times the whole thing. I just find sometimes students forget to distribute the 1/16. So if I put it here, they usually don't forget. So now 1 squared minus 1 to the 8th. Well, that's not going to be so bad. Let's see. We'll work out inside the parentheses. We've got 2 squared is 4 minus 1 is 3. So it's 1/16 times 3 to the 8th minus 1/16. Notice inside 1 squared minus 1 is 1 minus 1 is 0 to the 8th. So that second piece just goes away. The first piece is a really big number. I'll multiply that out in my calculator. Let's see. 1 divided by 16. And then times 3 raised to the 8th power. And I get 410.0625. I don't know how many decimals they want us to go to, but I didn't round that off at all. It actually ends after those 4 decimal places. In the book, they're going to write that answer as a fraction. And as a fraction on my calculator, if I just go math, turn it into a fraction, it is not a very nice fraction, 6,561 sixteenths. So the 3 to the 8th was the 6561. And then the 1/16 on the outside just gives us that 16 on the bottom. Anyway, I'll box both of those. I don't know on the computer how it would ask you to write the answer. Hopefully just as a decimal, because actually you could do that fraction in your calculator without too much of a problem, because that second piece just went to 0. You didn't have to add or subtract fractions this time, so it was not too bad. But anyway, that's the whole idea of integration by substitution. So for this semester, we're actually done with our methods of integration. We have one more section to go, and I'm going to show you an application of integration, which is from economics. It's producer surplus and consumer surplus. So we'll see that next time. But this time, remember, the integration using the technique of substitution is whenever you see something that if you were taking the derivative, you'd have to do the chain rule, okay? So you've got an inside function. So we let u be the inside function, and then we have to go through the steps to do the integration. All right, hopefully that helped. Do some examples, make sure you understand this so that obviously you can do it on the test. And then that's it. I will talk to you more next time. Have a great day.